we consider a very interesting example. And suppose f is a map from Rn to Rn, which is C1, and satisfies the following conditions. The first condition, for any x in Rn, the Jacobian derivative, Jacobian determinant of f at this point is not zero. The second condition is that this limit, when x goes to infinity, the norm of fx goes to positive infinity. Then f is surjective. The image of f is equals to Rn. Okay. So this problem is very important, because this means for any b in Rn, there exists x such that fx equal to b. That is to say, fx equal to b, this is a equation, has a solution, solvable. Therefore, as I emphasized previously, solving equation is a central topic in mathematics. So this kind of problem are very interesting. Okay. Now, we prove this result, and the idea will be used later in our study of the inverse function theorem. So it's good for us to have a look at this idea. So for any b in Rn, we want to find an x such that fx equal to b. For this purpose, we consider a function phi, a function phi defined in Rn. The value of phi is half of the distance from fx to b square. That is half of the sum fix minus bi square, where fi and bi are the components of f and b. So because f is C1, so fi, f1, f2, fn are also C1. Therefore, it is easy to see that phi is C1. Phi is a function continuously differentiable. Now we will compute the partial derivative or the gradient of phi. What's the gradient of phi is? We compute this. To compute the gradient, we compute the partial derivative of phi with respect to xj. So the partial derivative is easy to compute. This is I from 1 to n, and fix minus bi square. And it is not difficult to see that this is the square and will produce n2, and cancel with the half in front of the sigma summation. So the result is that I from 1 to n fix minus bi, then the partial derivative of fi minus bi with respect to xj, that is djfix. So what's this? This is precisely f1x minus b1 fnx minus bn. Then the Jacobian matrix of f, of the map f. Here is d1 f1, d1 fn dn f1 dn fn. The derivative in this matrix are taken at the point x. Okay, so this can be written in a compact form. This is precisely fx minus b and f prime x. This metric is just the Jacobian metric of f at the point x. In our notation, this is f prime x. Okay. No. So the gradient of G phi at the point x is d1 phi x dn phi x, which is f1x minus b1 fnx minus bn, then d1 f1 d1 fn dn f1 dn fn. All the partial derivative in this matrix are taken at the point x. As you can check this equality, okay, here, not difficult. And the right hand side, what's the right hand side? The right hand side is nothing but fx minus b and the Jacobian matrix f prime x. Okay, so we have compute the derivative of the gradient of phi at any point x. Okay, now how to apply the condition as our assumption? Here we have an assumption that f, the limit of f, the norm of f x at infinity is positive infinity. From this we see that phi x is half of fx minus b squared. Of course, by the triangle equality, this will not less than half of the norm of fx minus the norm of b, then square. Because fx goes to positive infinity and b is a given point, so we see that this goes to positive infinity. Okay, therefore, because phi is C1, of course phi is continuous. A continuous function has a approach to positive infinity at infinity must attain its minimum. Okay, this is a problem in our quiz. Okay, so a very important consequence is that there exists a Xi in Rn such that phi Xi is the minimum of phi x. Okay, the function phi attempts its minimum. This minimum, of course, is the critical point of phi. So we see that 0 must be the gradient of phi xc. But this, by our previous computation, the gradient of phi xc is f xc minus b, then the Jacobian matrix xc. Okay. Now our another assumption is that the Jacobian determinant, which is the determinant of the Jacobian matrix, is not 0. In other words, this matrix is invertible. This is an n by n matrix, is invertible. So we can apply the inverse matrix of f prime c from the right on both sides of this equality. We obtain 0 equals f c minus b, or f c maybe b G is f C belongs to the image of f. Okay, so for any B in Rn, we conclude that B is the image on the F at some point. So this proved F is surjective. Okay. So next we consider this idea introducing this function phi and find its minimizer to draw the conclusion is very typical and useful, and we will use the idea in our proof of the important result inverse function theorem in our future lecture. Okay. So we consider another important concept, the so-called case order approximation. Okay, so suppose f and g are functions defined in a neighborhood of A. So we say that G is a case order approximation of f. This is a definition if the limit h goes to 0, fa plus h minus ga plus h. The difference between f and g it should be small, and this is not only converted to 0, even divided by the the norm of h to the power k, it should be equal to 0. If this limit is 0, then we say that G is a case order approximation of f. Of course, you can also say that f is a case order approximation of G. Okay, so this means that near the point A, because h goes to 0, near the point A, f and G are very close. Their difference goes to 0. Not only goes to 0, even after dividing the very fast go to 0 fast quantity, the norm of h k. Okay, even divided this very small term, the limit is still 0. Okay, so this is the meaning of case order approximation. Of course, if we will study the function f, we want to find a simpler function g to approximate f, so that we can draw some conclusion about f by investigating g. Okay, so we want g to be a simple function. We want g simple. So what's the most simple function? Of course, the polynomial is simple. So we use polynomial to approximate f. This is just the result of Taylor formula. So we have an example. If f, in the definition of case order approximation, we have no regularity assumption on f and g. They can even be not continuous. But if f is good, say ck, then we take g a plus h to be L from 0 to k, L, the partial derivative of f with respect to x1, j1, j2, jl at the point A, and h, j1, h, jl. So this is the Taylor polynomial of f at the point A. We take g to be the Taylor polynomial at the point A. Then by the Taylor formula, which piano remainder, that is the HK, we know that FA plus H is GA plus H plus higher order infinitesimal of with respect to H, the norm of H to the power K. This means FA plus H minus GA plus H divided by the norm of K goes to 0. So by definition, this G is the case order approximation of F. Okay.